Hello. In today's video we are going to take a look at how to connect up to 8 LEDs to our microcontroller. We will start with just one LED and then move on to 8 LEDs. One thing to note is the LED is a polarized device. This means it has a negative and positive connection and will only work if the power is supplied correctly. We need to first identify the negative leg of the LED. The negative side also has a shorter leg, if they have not already been cut. It's easy as there is a flat edge on the body of the LED. You need to look carefully. I find this is the best method. Here you see the edge. This is the negative side connection. Here we take a closer look at the LEDs and some terminology. The flat edge is on the body of this LED. It is also the short leg side. This side is the negative connection. But it is also sometimes labeled as KK, means cathode, which is another name for negative. The other side is a positive connection. A positive symbol might be used, but also it could be the letter A. A stands for anode. In electronics, we love to use loads of different names and symbols for the same meaning. We often need to look at circuit diagrams, and for this, we would use a symbol that looks like this. The flat line on the symbol matches the flat edge on the LED body. Therefore this would be the cathode and this side the anode. The LED only allows current to flow in one direction. It blocks it in the other direction. When the current flows through it, light is emitted. In the following examples, we will connect the anode pin to our microcontroller pin, and the cathode to the ground of the Arduino board. For now, connecting one LED is very easy. We simply connect the leg of the flat edge to the ground pin. We actually have a few ground pins that are all the same, but I will use the one on this side for now. It's labeled GND. The positive leg will go to pin 13 like this. There we go. Connecting one LED is very easy at this stage. As always, I double-check the connection is correct. Now we can connect our board to the USB port. Wow, the LED is already flashing. This is because the last program I uploaded already made pin 13 turn on and off. So let's actually connect the LED to pin 12. This will give us the challenge to make the LED work from pin 12 instead of pin 13. Let's open our Arduino software up. This is the bare minimum code all programs must include. Remember, these are comments. I'll remove them for now, but you could add your own commentary by using the 2 forward slashes. We will now name our port numbers to make it easier to know what is connected to them, by using a text name instead of a plain number. Last time we used an int. This is actually a bad idea. This is because it uses up some dynamic memory, and there is not much available. The variable or int is perfect for storing numbers that change often. For example, if we need to count how many times a button is pressed, or keep track of time or seconds. As our LED pin number will not change, the correct method to name the pin number is using a define. The method to do this is type #define in all lowercase. Then the text name for the item, followed by the number of the port we are using. Now every time we type LED1, it will be replaced with 12. Note there is no semicolon or equals sign here. Next. Do you remember? We need to set up the ports as inputs or OUT/PUTs. We will only need to set up OUT/PUTs in this example. Type pin mode with a capital M, open bracket, then the name of the port, comma, then output in all capitals, end bracket. If you've typed it correctly, notice the colors. The first part is orange, The text name is black and the instruction is blue. We can now enter in our code for the looping part of the program. We'll do the same as in the last example. Make the LED flash on and off. So we'll type digital write with a capital W. Then inside the brackets, we'll have LED 1, which is in fact pin 12, then comma high. Then a delay so we can see that is in fact on. 1000 milliseconds seems good for now. So that is in fact 1 second. Followed by another digital write LED 1 low. We'll finish off with another delay. If we didn't finish with another delay, we would simply have the LED go off for so little time we would not see it. You should have a play with these numbers. OK. Let's now check our settings. The correct COM port is selected. I currently need to reselect the Uno board. I will also need to save it. And now we can upload it. Remember, we will see the TX and RX LEDs light up if it programs successfully. Great. We now have our LED connected to pin 12 flashing. Let's now connect a second LED to pin 13. If we are cheeky, we can hopefully fit a second negative leg into the same port as our first LED. There are some more ground pins on the other side of the board, but they will not easily fit as the legs are too short. So we'll just double up for now. The positive leg will go into pin 13 instead of 12. It's a tight fit, but it just about works. Then we need to go back to our software to modify the code to make both LEDs work. So back in the programming space, we simply add a new defined LED. This time I've called it LED 0 and it is on pin 13. We will also need to set it up as an output pin. Just the same as the other, but with LED 0 instead of 1. I find just copying and pasting the lines of code is the quickest. Use the Control key on the keyboard. It's the one labeled CTRL. Highlight the line of code to copy, hit Ctrl and C at the same time to copy. Pressing Ctrl and V at the same time pastes. Then we only need to change one number instead of typing out the whole line of code again. Then we will duplicate the lines that actually turn the LED on and off, with the updated label for LED 0. Again, copying and pasting these speeds things up. OK. We are ready to upload it. Press the download button. There we go. We now have both LEDs working. But let's say we want them to flash alternating. We just pop back to our software and make a very quick mod. We just change one from high to low, and the other way around below. Re-upload, and now we can see the LEDs flash in an alternating pattern. Now if we want to change the flash speed, we could change the delay value, but as the code becomes more complicated, this becomes more work. Imagine you have the delay 10 or more times. You would need to modify them all. Let's use the int method. Make a variable named delay time, and set its value as 500. As shown here. Now we can change the 1000 values in the delay brackets and type in delay time there instead. Now if we want to change the delay time, we can change them all at the same time by modifying the delay time value at the top of the program. Now the LEDs flash quickly. If we need to connect lots of LEDs to the board, we might need to use a breadboard. It is a prototyping tool that allows us to form electrical circuits without using a soldering iron. The main disadvantage is that you need to learn how it works. Or at least how it's wired inside. You simply stick the legs into the holes, but you need to ensure they are in places that allow the circuit to form. Here is a picture showing how the holes are connected internally. The green lines show which holes are connected. The next thing we should consider is our microcontroller puts out 5 volts on its pins. This is in fact too much for our LEDs. Consider when our output pin 13 goes high, 5 volts is supplied to the LED. The LED actually runs too bright. Over time this could cause the LED to burn out, or shorten its life considerably. Therefore we need to add a current limiting resistor, as drawn here. It will go between our output pin, to let the LED anode, then the lead cathode will connect to the ground. We will use Ohm's law to calculate the resistor value. But we will need to know some facts about our LED. Mainly what is its ideal voltage, and how many milliamps should it be supplied with. The only way to do this is to find its technical specifications. We should note this when we buy the LEDs. I got my LEDs from Rapid Online, so I will find the data there. Here I find my standard red LED has minimum voltage of 1.7 volts and a max of 2 volts. I think 1.8 volts is a good value to work with as it's between these two values. I also note that the LED should have 30 mA flow through it. Great. So now I must calculate a resistor value to allow this condition. So the LED should have 1.8 volts across it. And we'll also want I to equal 30 mA. What will the value for resistor be? R. Ohm's law is V over I times R. As the LED wants 1.8 volts, the rest of the 5 volts will be dropped over the resistor. That means 5 volts minus 1.8 volts leaves 3.2 volts across the resistor. 30 mA will flow through both the resistor and LED. Therefore 3.2 volts across the resistor, divided by 0.030 amps through the resistor, equals 84.2 ohms. I don't have any 84 ohm resistors, so I will choose one that I have, that is slightly bigger. That is 100 ohms. This will mean slightly more resistance, thus less than 30 mA, but it will keep the LEDs safe from burning out. We will now connect up the LEDs and resistors using the breadboard and some wires. Each LED and resistor pair should be wired as shown. Each LED resistor side will go to a different pin on the Arduino, but as all the grounds are connected together they can share a single ground wire. If you are confused by using the breadboard, you should watch some other tutorials on breadboards. They are a very important tool in electronics. Now just repeat the connection for each of the 8 LEDs. You may need to bend the legs a little to make them fit into the holes. I am leaving some space between them so the legs do not touch and short out. Once all the LEDs are in, I can add the resistors. All the ground are connected. I will put the single ground wire back to the Arduino ground. Now we add a resistor for each LED. Again taking care not to touch wires. Then we can use the wires to connect each row into a pin on the Arduino. All done. Now to modify our code to run these LEDs we need to define each LED with a pin number like so. It's exactly the same as before, but in total we have 8 defined LED ports. LEDs numbered 0 to 7, using ports 13 to 6. Again I use the copy and paste shortcuts to speed things up, and then manually change the LED and port numbers. Job done. Then guess what? I need to set each up as an output pin. Again copy and paste the line of code and modify the numbers as required. To make it a bit clearer, I can add several in a single line as long as they are split up with the semicolon. There we go, 8 in total, with their appropriate names. In the loop we will do the same. Copy and paste so we have 8 sets of digital write commands. Change the LED numbers as needed. Then we do the same for the second group below. I seem to have deleted the delay time, so I'll add that back in. Then I can manually go through these digital write commands and change all the first batch to high, and all the second batch to low. Let's upload and take a look. There we have it. All LEDs are flashing on and off. In reality, we might want some different patterns here. So let's try that. If we modify our two sets of digital writes with alternating highs and lows, we can have a pattern that flashes like this. Finally, we could have an example where we want one LED to light up, that moves across the 8. This will be more complicated, but again copy and pasting is our friend. First of all, I will change all of these digital writes to low. Then I will copy and paste this set, along with a delay 7 times. So now we have 8 sets in total. Now for each set I will set only one LED high. As I move down the sets I will change the one LED that is high so it moves across. For example, in set 1, only LED 0 is high. In set 2 only LED 1 is high, and so on. Once modified we upload and the result is this. So there you have it. We have managed to run a single LED all the way up to 8 LEDs. We have simply set the various outputs either high or low to get the desired pattern. If you found this useful, please hit that like and subscribe button. In the next tutorial, we will learn about the serial monitor feature and how to connect some analog devices. Goodbye for now.